Hello class, I hope you're all doing well. My name is Richard Zins and my partner's name is Brian Figg. We are going to be presenting on The Dancing Woolly Masters by Gary Zukov. So we structured our presentation a little differently than some of you may have. Instead of me giving the first half of the book summary and Brian giving the second half of the book summary, I've decided to give the entire first half, or the entire book summary, as well as some basic mathematical, philosophical points sprinkled throughout. And then Brian, in part two, is going to go over into a deeper dive of some of the harder to understand mathematical, scientific, and philosophical implications of the book. With that said, let's get started. The Dancing Woolly Masters by Gary Zukov is about modern physics, at least as it was understood in 1979 when it came out. Basically, the Dancing Woolly Masters focuses specifically on quantum physics and quantum phenomena and everything related to it. It tries to relate many of the topics in quantum physics to Eastern teachings and Eastern texts, specifically Asia and India mainly, and the cultural aspects in that region. Overall, one of the main philosophical points that Zukov wants to get out of the book, we believe, is the idea that philosophy, science, and mathematics are more interwoven than what many scientists would have you believe. But this has drawn up much controversy around the book, as many people in the community at the time felt that his book was, they would call it pseudoscience. Today, it seems to be better received. So, the book begins with Zukov discussing his time at a physics conference, which prompted him to actually start researching much of the material that he needed for this book. At this physics conference, he met a Tai Chi master who said that when he studied physics in Taiwan, they referred to it as Wu Li. Now, Wu Li, translated into English, means patterns of organic energy. Zukov thought this was a great definition for physics at many different aspects, but specifically, he also believed that this idea of patterns and organic energy and just kind of that whole phrase could almost be applied at the subatomic level as well as in other abstractions within physics. These ideas and how it related to Tai Chi and Eastern culture in general fascinated Zukov. He also then begins to discuss, after this, the differences between Newtonian physics and quantum physics and how they relate. The biggest thing that you guys should understand about this is that the laws of Newtonian physics start to break or contradict what we know about the subatomic level, meaning what we know about quantum physics, or subatomic particles in general. But yet, so much of Newtonian physics still does a great job at explaining other aspects of the universe, not at the subatomic level. I believe this is best shown with a quote from Zukov's book. He states, "Woolly masters perceive in both ways, the rational and the irrational, the assertive and the receptive, masculine and feminine. They reject neither one nor the other. They only dance." To me, this shows that you can still use the concepts of Newtonian physics and quantum physics separately and correctly without fully understanding how they work together. As for example, Newtonian physics was able to bring us to the moon, right? But we know it doesn't really work the laws of Newtonian physics don't necessarily fully apply to subatomic particles, and they contradict what we know about them. So next, the author starts to describe a common theme within Eastern literature, and I'm going to quote for you what he says. This theme is, "To dance with God, the creator of all things, is to dance with ourselves." And here, I believe what he's saying is that he believes that each of us shares a role in the creation of our physical reality. This then leads him into a discussion on the duality between waves and particles, which Brian will talk about a little more in depthly in his part, but I'll give you a brief kind of overview right now. Right, there's this notion that waves may be made up of particles, right? Or maybe particles are also waves, and how those two are related. I believe that we have a similar duality between science and math, and this raises a good philosophical perspective on mathematics, right? Specifically about mathematical objects. For example, let's examine an arithmetic equation. 1 plus 1 equals 2, right? One finger plus one finger, 2 fingers. In a way, 2 fingers right here and 2 fingers right here are the same mathematical object, but they're also uniquely distinct. Just like each side of the equation, if you were to write it out, 1 plus 1 equals 2, on each side of the equal sign, 2 is a uniquely different statement than 1 plus 1. Yet they may represent the same things. So we see this duality in math all the time. And it's a great link between both science and mathematics as well. Zhukov also, soon after discussing the duality between waves and particles, brings up Schrodinger's equation. Now, Schrodinger's equation is an equation that is a partial differential equation that describes the wave function of a quantum mechanical system. So one of the main points that the reader should take away from here is that Schrodinger really did believe that his equation represented real particles. It wasn't just some mathematical concept. In fact, he imagined that you could take this wave function and you could plot it out, right, however it looked, and there would be subatomic particles. Specifically, he believed that there would be electrons just spaced out evenly along this wave function. And so that's a really interesting point. But an even more interesting point that when this was accepted within the scientific community and more people started to study subatomic particles and electrons specifically, is they found out that due to Heisenberg's uncertainty principle, they could not observe an electron without altering it. This was a fascinating discovery, but also a pretty hard wall. This leads Zhukov into discussing that because we can't meaningfully measure subatomic particles without losing some data or without altering some data about them, that he believes that quantum mechanics cannot be an exact science, which is a very interesting philosophical standpoint and juxtaposes what a lot of other scientists believe. Because of this, the boundaries of objectiveness and subjectiveness in quantum mechanics is blurred. Later in the book, Zhukov takes some time to discuss some aspects of physics that may seem like nonsense when you try to think about them with classical mechanics, but can actually may be explained by quantum mechanics. Two prominent examples of this are the speed of light, as well as the idea of space-time. So let's talk about the idea of space-time, right? The idea, one might think that space and time are separate entities, but both Zhukov and before him, Einstein, believed that space and time were one. Specifically, you might refer to this as the space-time interval. And an interesting point that Zhukov brings up is that the calculation to calculate the space-time interval is very similar to the Pythagorean theorem. For example, the Pythagorean theorem, as we all know, is a squared plus b squared equals c squared, while the space-time interval is t squared minus x squared equals s squared. So, while they obviously use, while the space-time interval uses some highly different constants, it is interesting how, in terms of mathematics and philosophy, how they are both able to use fundamentally the same mathematical truths and mathematical operations to form some fundamental aspects of the universe. And my partner and I, as well as Zhukov, I believe think that's very profound. Zhukov then begins to go into some more ideas of Eastern literature and how the concepts between philosophy, religion, and scientific ideas being separated is very Western ideology. In Eastern ideologies, these concepts are interwoven together. For example, Zhukov states that Eastern literature speaks repeatedly of dancing energy and transient impermanent forms. This is strikingly similar to the physical reality emerging from quantum physics at the subatomic level. At the end of the section, Zhukov also starts to go into the fact about how, as we learn more about quantum physics, we start breaking aspects of Newtonian physics. And he argues, while this makes things harder to understand in the short term, in the long term, it contributes to our enlightenment of knowledge as it relates to our comprehensive understanding of the universe and reality, which is very important. Okay, so towards the end of the book, Zhukov really begins to get into the nitty-gritty and start to explain the interactions between subatomic particles in more detail. So if you hadn't caught on before this point, right, quantum physics is all to deal with subatomic particles and the interactions they have. These interactions they have are called events. So some examples that Zhukov described in his book are what happens when a photon collides with an electron, or when an electron gets close to a positron, and what happens. Zhukov refers to all these events in his books as the dance, which is obviously an homage to the Tai Chi masters and their culture. One of the other major concepts that Zhukov goes over towards the end of the book is the idea of quantum theory. For those who don't know what quantum theory is, I'm going to quote Zhukov here in his words. In other words, all particles exist potentially with a certain probability as different combinations of other particles. Each combination has a certain probability of happening. This probability is the study of quantum theory. So quantum theory can also have a lot of philosophical math implications, right? So it uses probability in a sense to determine the state of a particular subatomic particle. In a sense, we can then ask ourselves, right, does this suggest that if these probabilities are accurate that we're able to compute, does that mean we can now predict universal randomness? If these probabilities are so good, does that imply, and so consistent with the way the universe works, does that imply that math was discovered rather than created? These are some important philosophical math questions that arise when thinking about quantum theory. So, this brings us to the end of the book. Zhukov ends the book by discussing how physics and mathematics are not nearly as separate from philosophy as many scientists will have you believe. For example, one of the reasons that he comes to this opinion is because both philosophy and quantum physics are trying to discover what reality is really composed of, and in a way, how the universe works. He also believes this because, in a way to fully comprehend some parts of quantum physics, some scientists may have preordained philosophical opinions about how the universe works. And this goes back to his point earlier about how the lines between subjective and objective in quantum physics are blurred. Lastly, Zhukov explains that scientists love facts, but he believes in order to have a more comprehensive idea of the universe as a whole, and how quantum physics, quantum phenomena, physics in general, mathematics, sciences, philosophy, how it all works together, we may have to accept more opinions that may not be observably confirmable, like in the case of quantum mechanics. Overall, my partner and I enjoyed the book a lot. I think that it was a really good explanation of quantum physics in a detailed manner that didn't require a lot of subsequent pre-knowledge. And I think he did a great job at that. There are times where the book feels like he is going into topics that seem unrelated, but if you reread it a couple times and go back, you can all see how it's connected. And it's clear that he put a lot of thought. He also references the works of some great influential scientists in physics throughout history, and uses their findings to make some really profound descriptions. And it was really a great read, even if, like I said, at some parts it may feel slow or it may feel unrelated. It does all tie in at the end. So, as I stated in the beginning, my partner is now going to discuss some more philosophical implications as well as mathematics and scientific concepts in some more detail.
Hello. So, as a forenote to the lecture that I will be providing, part one is my partner Richie or Richard Zins. He will be doing the general overview of the book that we chose, The Dancing Wooly Masters and the Table of the Nucleotides. I, however, will be doing a more in-depth view of some of the philosophical points that arise from the book. So you should realistically watch his video first before viewing mine, because he will provide the context for the given assignment that I'm doing. Alright, with that, let's get started. So early on in the book, the author more or less brings up a interesting point that I thought was worthy of note, and that was that science in the early days was very detached from philosophy, whereas nowadays, philosophy is almost intertwined with the idea of science. And one of the interesting ways that information presents itself is the idea of quantum physics. So, some of you may or may not know from your physics classes, if you've taken any, that more or less light can be either a particle or a wave. And and this was really highlighted in an experiment called the two slit experiment. And the two slit experiment was trying to find it was trying to find whether a particle acts or a light or a wave or both, and why. Well, what the result of the experiment found is that it's almost wholly dependent on the presence of an observer or a detector, as it's otherwise known. And as a result, this detector can influence the outcome of the experiment. And this presents an interesting question. So, if a observer can directly change the outcome of the quantum state, does that mean that we as humans who are actively observing this phenomena are themselves directly affecting the quantum state and therefore the universe itself? So, and this was really fascinating to me, is because many of these questions were not able to be were not arising from previous mathematics, like 1600s, 1700s, when science was really more of, okay, how does the physical world exist? You were studying more natural phenomena rather than universal phenomena. And it's fascinating to see that, that we as people can directly affect the universe itself just by observing the quantum realm or phenomena, whatever you want to call it. And so let's move on to another thing. Our book has to be complemented by something called the table of the nucleotides. And so, from a philosophical point, we know early on in existence, early on, with Mendeleev's table of the elements that didn't end up holding water, it ended up becoming a periodic table of the elements. That they were studying physical properties of the elements early on before they necessarily had a understanding of what is a proton, what is a neutron, what is an electron. They were doing it based on certain properties and the weight of the given atom. And that sort of changed when we discovered those particles and the idea of isotopes, that I could have three different forms of hydrogen. Like, we could have protium, which is just normal hydrogen that we think of, a proton and an electron, and then we could have deuterium, which is a proton, a neutron, and an electron, and then we can have tritium, which is even bigger, which is a proton, two neutrons, and an electron. The idea of having these different permutations of the same element showed that our scale of the whole thing really needed to be expanded, because how do you account for it? Well, the periodic table did this by accounting for the lowest common denominator, that being the proton. You count how many protons are in a given atom, and then by altering the amount of neutrons, or I'm not sure if electrons are changed as well, you would get a different atom, more or less, or you would get a different atom, but of the same element. And this is rather interesting because you can do the lowest common denominator, but it's very hard to display all the other permutations. So this is where the table of the nucleotides comes in. And it's this idea that this whole thing could be bigger than we possibly know. And the reality is that the table of the nucleotides is infinite. As it is right now, our chemists are capable of predicting up to, I think it's 125 or 130 in the element range of existence. And there's an island of stability in the 120s based on our quantum mechanical models. So this implies that theoretically we could get infinitely high, up to, I think, the Chandrasekhar limit of a given atom. The Chandrasekhar limit is it's dependent on how much mass you have in a single space. If there's too much, then essentially it's more or less becomes degenerate matter. However, this implies to me that we ourselves are that our universe ourselves are infinite. The things that we're discovering that we thought were limited in scope are actually much larger. And this is where philosophy directly intervenes, in that where we thought before that we ourselves that we cannot directly influence the universe itself, where we're just studying it, we're in this fish tank, more or less. Many of these atoms on the table of the nucleotides are manufactured. They're artificial in nature, implying that we ourselves can actually create things that wouldn't typically exist in the universe, which means that there has to be a reasoning behind this, and that answer is provided by philosophy. So that's the second thing I wanted to bring up. And the third thing that I wanted to bring up was the concept of the general relativity. And this is fascinating because it's all dependent on one's perspective. We sort of in our minds have this idea of simultaneousness, that two things can happen at the same time, when in fact that isn't true according to Einstein. Because if you have two different people equally distant apart and view a source of light that is equally distant apart between both of them, do they both see it at the same time? And the answer is no, because they do not occupy the same inertial reference frame. There will always be some form of interference that prevents them both from viewing it at the same time, unless they're but like two people in one body. That's the only way you could experience the same thing twice. And as we know, you can't stuff somebody inside of another person. It just doesn't work. And so it's interesting is that we can have these concepts of these things existing, but they can never truly exist. And it's even greater when you look at the grand scheme of things. Instead of just two people, what about two planets or two galaxies, right? You can scale this up, and the same thing holds true. And it's this idea that the science is directly intertwined with philosophy now, in that it's no longer just about us in the fish tank, in our universal fish tank, just existing. It's more about, well, these things are the walls of the fish tank themselves. They're the structure of the very universe we're getting into. The ideas that are being presented in nowadays science are more or less the culmination of human thought coming together, and creating these ideas. And so, I mean, it's going to be interesting to see the future. Just this book has really, woken up my eyes to the idea that maybe there is no limit. Maybe we ourselves are just coming to this point where once we understand the universe itself, the limit of the universe is ourselves. It's how much we want to discover, how much we want to find. And I truly believe that's the future in store for us. Anyway, with that, this concludes the part 2 of the lecture. Once again, reference my part 1 partner, Richard Zins, for context for this. With that, thank you.